Hi everyone, thrilled to have you back with us at educator.com. This lesson is going to be an introduction to electromagnetic induction. So, our objectives are going to be explaining how a changing magnetic flux through a loop of wire can create an induced electromagnetic force, or an induced potential difference. Calculate the magnetic flux through a loop of wire, calculate the induced EMF using Faraday's law, find the induced EMF in an expanding or contracting rectangular loop of wire, utilize Lenz's law to determine the direction of the induced current flow, and finally, explain the basic operation of an electric generator or motor, something that we touched on last time. All right, so induced EMF, or electromotive force. Charges flowing through a wire create magnetic fields. Now, changing magnetic fields can cause charges to flow. They induce a current in a process known as electromagnetic induction. The potential difference created that causes that current to flow by that changing magnetic field is known as the induced EMF, or electromotive force. Now, don't get fooled here. Even though it says electromotive force, it's not really a force. It's a potential difference. It's a source of potential difference that causes current to flow. The amount of magnetic field passing through an area is known as the magnetic flux. That's given the Greek symbol phi. Oftentimes, you'll see that written as phi b for magnetic or phi m. And the units of magnetic flux are Webers, where 1 Weber is equal to 1 Tesla meter squared. So, finding the magnetic flux. The magnetic flux through a given area A due to some magnetic field B can be determined as the flux is equal to the magnetic field strength times the area. So let's take a look at induced EMF in a rectangular loop of wire. The induced EMF, let's find its magnitude, is equal to the change in the magnetic flux divided by that time interval. Well, that magnetic flux, that's just going to be change in BA, the magnetic field strength times the area there divided by that time interval. But if this is a constant magnetic field strength, that's B delta A over delta T. But the area is going to be this length times that x direction. So that's going to be B, that x dimension, delta Lx over delta T. But again, in this diagram, L isn't changing. It's a constant. So we can pull that out of the delta, and we get BL delta X over delta T. What's delta x over delta t? Well, that's velocity. So that's just BLV, the induced EMF, due to a rectangular loop of wire moving with some velocity, expanding with some velocity. Now, Lenz's law is probably the toughest part of electromagnetic induction, but once you understand it, it's so simple. What it states in words is the direction of the induced current always opposes the change in flux. Putting it in words makes it so much more complicated than just doing it and trying to understand what's going on. Here we have a magnet, and we're going to put it through a loop of wire. And let's assume that our magnet, we're moving it downwards. Well, the flux from our magnet, remember the magnetic field is going to run from north to south. So coming out of the north, we have our flux going that direction. And as it gets closer and closer, what's going to happen due to the magnet moving this way? Well, we're going to have more flux going down through that hoop. So pushing this down is going to put more flux through that hoop. The current wants to oppose any change in flux through the loop. So if we're putting more through here by moving this down, the induced current wants to go the opposite direction. So we're going to think of this as if we are trying to put some flux the other direction. Now we can use our right-hand rule and say, well, if we've got magnetic flux going that direction through the loop, wrap the fingers of our right hand in that direction, and that would only occur if we had current flowing in that direction in the wire. Pushing the magnet down creates more flux down through. We want to oppose that change, so we will have flux going the opposite direction, and then figure out, using the right-hand rule, the direction of the current, using that opposing magnetic flux, because the direction of the induced current always opposes any change in flux. Let's take a look down here at this example. We're going to do the same basic idea, but now we're going to move our magnet this way. Once again, the magnetic flux was going this way, down through the loop, but as we pull the magnet away, as we move it up away from that loop, we're going to have less magnetic flux going down through there. Well, the induced current wants to oppose that. If we have less going down, it's going to want to oppose it by having more flux going down. Now we can use our right-hand rule again, point our thumb of our right hand in the direction of that magnetic flux that's opposing, and we would get a current flow by the right-hand rule that's now in this direction, using Lenz's law to determine the direction of the induced current. Well, now let's flip the magnet around and see what happens. Over here on the right, the upper right, let's assume that we're pushing the magnet down through that loop again, but now that we know magnetic field lines run into the south. So as we are pushing this down in through that loop, what we're actually doing is we're creating more magnetic flux. It's pointing in this direction, so we want to oppose the magnetic flux in that direction. As I point my finger in the direction of the opposing magnetic flux, use the right-hand rule, I can determine that the current should be moving that way around the loop. Or finally, the last situation, let's assume we're pulling the magnet up out of that loop. Again, the flux goes in, the field lines go into the south. So as that's going up this way, we are reducing the magnetic field going through this direction. We're going to have an induced magnetic field that wants to keep that going that way. We want to continue in the state that it was, and if we're having less going up, the induced current is going to want to put more going up, so it stays in the same state. Now we can use our right-hand rule again, point the thumb of our right hand in the direction of that opposing magnetic flux, and I would get then a current that is flowing in roughly that direction. So that's Lenz's law. Takes a little bit of practice, a little bit of doing, but it's a lot easier than chasing down those negative signs. All right, electric generators and motors. By turning a coil of wire in a magnetic field, you can generate an induced EMF because you're changing the flux through that loop. Generators use mechanical energy of some sort to turn the coil of wire, or to turn a magnet inside a coil of wire, to create a changing magnetic flux, and therefore create a source of potential difference. Think of hydroelectric power. Water moving spins spins either coils of wire or magnets around a coil of wire to change a magnetic flux, which is converted into an electric potential. Or steam power turns a fan. As that fan turns, it's going to turn a coil of wire or a magnet to change a magnetic flux through a coil. Nuclear power, same idea. Use nuclear power to create a lot of heat, a lot of steam. That steam is then forced through fans, which are then used in order to turn coils of wire or magnets, creating changing magnetic flux and therefore potential difference. Very, very, very common. And electric motors operate using the same basic principle, and we talked about them a lesson or two ago, how those work using the principles of electromagnetism. So let's do some examples. Find the magnetic flux through a circular wire of radius 0.2 meters sitting in a 3 Tesla uniform magnetic field if the circle of wire is tipped 20 degrees from the horizontal. So we're tipped just a little bit here as we come out of our surface compared to the magnetic field. We have an angle between them of 20 degrees. So our magnetic flux, phi b or phi m, however you want to write it, is BA times the cosine of the angle between those, which in this case, it's going to be B times the area. Well, we've got a radius, so the cross-sectional area will be pi r squared cosine theta, which implies then that the flux is going to be, well, B is 3 Tesla times pi. Our radius is 0.2 meters squared times the cosine of 20 degrees. So I get a magnetic flux of about 0.354 Webers. Centimeters is situated perpendicular to a 2 Tesla uniform magnetic field. After half a second, the magnetic field has dissipated completely. Determine the average EMF induced in the wire. Well, our initial magnetic flux is going to be BA, or B, times pi r squared, which is 2 pi times 0.025 squared, our radius in meters, or 0.00393 Webers for a single coil. Our final flux is going to be 0 because the magnetic field is dissipated. So our average induced EMF is going to be minus, well, we have to take into account our number of coils, n, times the change in flux divided by our time interval. Or minus 50, our change in flux, final minus initial, 0 minus 0.00393 is just going to be negative 0.00393 Webers, divided by our time interval of 0.5 seconds, or 3.93 volts. All right, let's try one more example. Looking at the current induced in a rectangular loop of wire, we have a U-shaped loop of wire which is connected by a conducting path on rails which moves upward at a constant 3 meters per second. So this piece is moving up at 3 meters per second. If the wire is situated perpendicular to a uniform half Tesla magnetic field, find the current flowing through the resistor. In which direction will the current flow? Well, first off, let's figure out that the induced EMF, E average, is going to be equal to BLV. Or that's going to be 0.5 Tesla times our length here, that's going to be 0.5 meters, times our velocity, 3 meters per second. So half times 3 is going to be 0.75 volts. Now, if that's situated here, we're trying to find the current flowing. This must have some resistance in that loop R. Well, I is going to be V over R, where our induced voltage is just going to be this 0.75 volts over whatever R happens to be for that circuit. And in which direction will the current flow? Well, to do that, we're going to do Lenz's law again. As V is moving up this way, we're getting more flux down through that area. It's getting bigger. We're getting a bigger flux. If we want to oppose that, in that case, then that means that our induced current is going to want to create a flux coming back out to oppose that. And by the right-hand rule, if I point the thumb of my right hand in that direction of the flux from the induced current, I find that that must be going counterclockwise. So the direction of the induced current would be in that direction. All right, hopefully that gets you a good start on electromagnetic induction, Lenz's law, and how we put all of this together. Thanks so much for your time, and I look forward to seeing you soon. Make it a great day, everyone.